I want to pick back up where we left off yesterday. And when we left off yesterday, we were just finishing example B there. Okay? So, as we were finishing example B, before we go into the next set, I just want to kind of remind you where we were, because I know some of those I wrote down as you guys were walking out, that kind of thing. But if you remember, the last one we looked at was this x to the third minus x. We did our extrema, our mins and maxes, we did our zeros, our x-intercepts, and then the part that we talked about, but I wrote down as you guys were walking out, so you did not necessarily get this, is that the shape of this graph. Generally speaking, as we look at the shape of this graph, it looks like an x to the third graph. If you look at the overall picture, it looks like an x to the third graph. But what's happening near the origin? As you look near the origin, my graph kind of has a downward slope. And so at that point, it looks like the graph has the same shape or slope of the y equals negative x portion. And that was the part I was talking about as you guys left yesterday. If I graph these three, I'm going to zoom this in for a moment so you can see. And I'll put that back out. If I graph these three. So right now, okay, I'm zoomed in. The first thing graphing is our graph of question here. The next thing, this is just your basic x to the third, so notice the same shape. And then I typed in the wrong graph. Hold on. Let me make that a negative x instead. Okay, so redo. There's the graph of question. The red graph here is just your basic y equals x cubed. And then this graph is the other portion, the y equals negative x. And do you see how the blue graph and that black line have the same slope there at the center? Okay, that is how it resembles both shapes. If you zoomed out, you'd be able to see the overall shape better. Okay, so that's what, when it talks about multiple, a graph being made of multiple monomials, that's looking at the pieces, and that's trying to break it down. Okay, that takes us into the bottom part of this page. And the bottom part of this page, we're going to look at options of what a cubic graph and what a quartic graph can look at. So when I say cubic, what do I mean by cubic? Yeah, when we say cubic, we're talking about a function where the largest exponent is a power of 3. And so those are options of cubic graphs. Okay, the basic one we know is this first one. This one right here with the extra loops, or with the extra mountain and valley, that's like what we just looked at, where there's an extra minus x term thrown in. Okay, if we had a negative here or something, it would just reverse. It would start high and go low, things like that. And those are things we'll be talking about. Now, so cubic is x to the third. What's quartic? X to the fourth. So there are a large variety shown, but that second row are all quartic options. Okay? The one we looked at yesterday was basically it was a variation of a parabola, right? It's a variation of a parabola, and that's the first one you see. These other variations that you see along the line are all just variations where there's other terms added. And those other terms, so like maybe an x cubed term, x squared term, x term, affect what the shape of the graph does. Okay? Now, a couple of things here. If the leading coefficient is negative, the graph will be flipped vertically. I'm trying to get zoomed where I want it here. So what's that mean? The leading coefficient is negative. Just think it like a parabola. X squared is right side up. What's negative x squared? Upside down. Okay? Same thing happens with x to the thirds, x to the fourths. If it's a negative, flip that graph upside down. So if your leading coefficient is negative, flipped vertically. So flipped upside down. Or reflected across the x, essentially. Now, important key before we move on to the back side. A polynomial function of degree n will have at most n minus 1 extrema and at most n zeros. Now, let's put that in language you can understand, because right now I'm sure it is gibberish, okay? So, a polynomial function of degree n. What do we mean degree n? How do you find the degree of a polynomial?
Exponent.
It's the term with the highest exponent, right? So if your highest exponent is an x to the fourth, that means that there are, it's degree 4. Now, so, for example, and let me use this example. Okay, if we pick degree 4, then notice what it says. It will have, at most, n minus 1 extrema. So what's that mean if it's degree 4? At most it would have 3 extrema, right? Does it have to have 3 extrema? No, the phrase is at most 3 extrema. And then it continues to say, at most, n zeros. So if it's degree 4, it can have at most 4 zeros. And what do we mean 4 zeros? What are zeros? Yeah, places it crosses the x-axis. Okay, so that's kind of your example there. These are all quartic examples here, yes? Give everyone a moment, make sure we're all caught up here. Okay, these are all quartic examples, yes? Do all of them have 3 extrema? Remember, what are extrema? Mins and maxes. This basic one right here, what's it have in the way of extrema? It has 1, yes, because it has 1 min. Okay, what about if we go look at this one over here? How many extrema does it have? 3, because there's 1 min, 2 mins, and 1 max. So you've got a total of 3 extrema. So min, max. Okay, some of the others are, other variations there. What about zeros? At most 4 zeros. Now, it says at most because it all depends on where this graph crosses the x-axis. So, for example, if I draw my x-axis right through here, what do you see in that particular spot? 1, 2, 3, 4 zeros? What if that x-axis was down below the whole shape? We could possibly have no zeros, right? So it all kind of depends on where the graph is drawn or whatnot. But that is a rule, and we're going to use that rule in some of our upcoming stuff here. But remember, if it's degree n, you have at most that many zeros, and at most 1 less than that many extrema. Questions before we turn the page? Okay, grab your calculators for this next part. Now, as you look at this problem, it asks us to superimpose the graphs of f of x equals x cubed minus 4x squared minus 5x minus 3 and g of x equals x cubed in successively larger viewing windows, a process called zooming out. Continue zooming out until the graph looks nearly identical. Take note of the window size. What are the similarities of the two graphs? Okay, so graph both of those on your calculator. And then notice how the same or how different they are. And then start using some of our zooming techniques. And really, we can just zoom out on this one and go from there.
My calculator, the graph window is messed up.
Can you just do a zoom 6?
I don't think a Zoom 6 would fix this.
Clear it and then clear it.
I'll look at it here in a moment.
I don't know if I well, no, because I got that.
What other graphing issues do we have?
He's trying it again.
Okay.
They told me to fix it.
Okay.
Clear all the graphs.
Good job, William.
Okay. It really is just some trial and error, isn't it? Okay. Are we working again these graphs? Minus all graphing issues of the day. I guess one advantage of sitting at these tables, you can cut our groups, we can help each other a little easier, which you can always help each other, but, well, my Algebra 2 kids have a test tomorrow, so it definitely will not be like this tomorrow. So, and I don't have time to change it between classes. So. Okay, guys, come back together here. Okay, so first of all, I can't fully see my graph here. And if I go to zoom out, does it go out way far on the first bat? It does go out pretty far, doesn't it? Okay, now this one's okay, isn't it? Okay, so that might be my best shot of seeing full view of what these graphs look like, yes? Do we know what y equals x to the cube looks like? Do we see the general shape of that other graph? Okay, how it generally relates to x to the third. Now, because there are other terms, that min is pulled down farther, right? So now, as we look at these, we're supposed to continue zooming out until the graphs look nearly identical. Did you stop here? I say I would go out again, definitely. To just zoom out, you can just hit zoom out and hit enter an extra time. Now, the thing is, we almost should work on changing our windows by hand, because you get to this point, and mine zoomed out so far that I can't even really tell what's happening, can I? Okay. They do look identical, don't they, almost? Okay. There's very few differences here. So, what window did it put me at? Yeah, it did put me at, it's a negative 160 by positive 160 window. If you wanted to play with those numbers some, you could play with those numbers to see what happens. If I zoom out one more time, right here, they're very close to being identical. If I zoom out one more time, I am so far out that you can't tell what's happening at all. And they are definitely looking identical.
It looks like a line.
Yeah. And honestly, if you don't watch the graph, it almost doesn't look like a line. Okay, and again, this is where changing the zoom features by hand might be a little bit better. But play in your calculators, okay? Now, so, some things to write down. First of all, I'm going to do a general sketch. My y equals x to the third graph looked like such, yes. My other graph, it goes up, but then it... Interesting noise. I know that's probably not even very accurate, but there's the idea. Sorry, I don't like those graphs, honestly. That's kind of where we begin at. By the time we get done, when I got to that 160, what was happening? They were looking almost, minus one little dip in the middle, they were looking almost like just both x to the third. And that's the idea of zooming out there. So, said take note of window size. So, things I noted, they're very similar at the negative 160 by positive 160 size. They are pretty much the same. And that last size that my calculator did is negative 640 by positive 640. What are the similarities of the two graphs? Well, what basic shape do they both have? These are both what types of graphs? Cubics, right? So if I take note of similarities, they are both cubics, meaning they both have the leading term of y equals x to the third. Okay, they both have that degree of 3. And then one other thing we can talk about with these graphs, because they are x to the third, what are the graphs doing? They are moving where? As we move from left to right, these graphs are moving up. Okay, so they have that general increasing feature. Even though, yes, that one, it increases, it goes down briefly, and then goes back up. Generally speaking, they are both increasing. So that's the other thing I'm going to note here, is that both graphs are generally increasing. I'm not going to specify and say increasing because they're not always increasing, or the one isn't, but they are close. Okay, you guys got what you need there? If you happen to have your book and you want to, open to page 188. I'm going to reference a chart on page 188 for this next part. If you don't have your book, I'm going to put my book on the screen. Or if you don't want to get your book out, I'm going to have my book on the screen. Okay? Now, we talked, I'm trying to think. We've talked a little bit about in behavior when we talked about horizontal asymptotes. You guys, that was in chapter 1, I believe, where we talked about horizontal asymptotes. So we talked about in behavior because in behavior is what is your graph doing as it goes to the ends. And so when I'm talking about going to the ends, I'm talking about going all the way left and all the way right. That's in behavior. Is my graph just going off along the x-axis, so it's going off along 0? Is it going way up high and going off to positive infinity? Or is it going way down low and going to negative infinity? Those are the types of things we're going to talk about. Now, talks here when looking at a graph, we can describe a function's in behavior based on where it's going as x gets infinitely large or infinitely small. We're going to use limits here. Okay, I'm going to have to fight the glare, aren't I? Let's see. Is that better? Yeah, I think that's better. Okay, so right now, as we look at these, okay, first of all, if you look up here in the top of this chart, it talks about for any polynomial function. So any degree polynomial function, the limits, and we're going to practice writing these limits. But the limit as x approaches infinity of f of x and the limit as x approaches negative infinity f of x are determined by the degree n of the polynomial and its leading coefficient. In other words, even if you don't have the graph in front of you, you can still determine what this graph is doing. Okay? Now, when we talk here, okay, so first of all, what do you notice about the top row? What kind of graphs are these? They're cubic, yes? These two graphs are cubic. We recognize them as cubic because, generally speaking, we're used to them starting low and ending high, or it could be vice versa. Now, as you look at that, in Algebra 2, we talked about up, up, down, down, up, didn't we? Or am I imagining things? In behavior? You did?
I did.
Okay. Do you guys remember how that went? Sounds familiar, but when we talked about a graph's in behavior, it could be up, up, such as in behavior here is up, up, because where are my two ends going? Up and up. Something like this, its in behavior was down and up because it started down and ended up. I know we did this in Algebra 2. Okay. So this kind of graph would have in behavior that is down, down. And what am I missing? This would be up, down. Okay? Basic review of Algebra 2. Now, we could look at that based on powers, based on signs. My up, up, and down, down. What basically did I draw? Parabola, yes? So that's basically an x squared, which means it has what kind of power? 2 is what?
Negative.
Well, no. These are both x squareds, or what else could this look like? Could that look like x to the fourth?
Yes, ma'am.
What's the comment about 2 and 4? These are both even. Now, what's different about this graph that has down, down? It's negative. But these powers are both still even. Okay. Now, what did I basically try and draw here? An x to the third. An x to the third. What am I trying to get you guys to say about x to the third? It has an odd power. And if it has an odd power, it's either up, down, or down, up. This has a positive x to the third, so it starts down, ends up. This is a negative x to the third, so it starts up, ends down. Okay, we did this in Algebra 2. I know, it's been a year, right? Although it hasn't been a full year, because this would have been second semester, definitely. Now, how that connects with what we're doing today. We're doing that same thing, except instead of using up behavior, or saying it's up, we'll say that it goes to positive infinity. Instead of saying it goes down, we're going to say it goes to negative infinity. Okay, so looking at this first example. This is an example of like an x to the third, and so that means this is an odd power. So as we look at this, over here, as I move to the left, where is my graph going? Down. So as x approaches negative infinity, that's saying as it moves to the left, my graph is going infinitely down. Infinitely down is expressed as negative infinity. What's happening as we move to the right on this graph? As my x values get larger and larger and larger and I move to the right, where's my graph going? Up. As it's going up, it's approaching what? Positive infinity. So as x moves to the positive infinity, it's approaching positive infinity. Those are the type of limits we're going to be writing, which is what I'm trying to show you in this chart. This graph, what's happening? As x moves left, so as x approaches negative infinity, where's my graph going? Up. Which what is up? Up is, it equals positive infinity. Here, as my x approaches positive infinity, so as I go right, where's my graph going? Down, so it's approaching negative infinity. Are we seeing how this works? Okay, so here's your other options. Okay, these are more like x to the fourth graphs, right? We would normally call this up in behavior. But in here, as my graph moves left, so as x approaches negative infinity, where's my graph going? Up to positive infinity. As x gets bigger, so as x goes to positive infinity, my graph is also still going to positive infinity. These two down here, notice we're still talking when n is even, and this will always be true based on even. As x approaches negative infinity, so as we go left, my graph's going down, negative infinity. Same thing over here, it's going down, negative infinity. So the connection to make, my top two graphs are representing odd exponents. My bottom two graphs represent even exponents. On the left represents where my first coefficient is positive. Okay. On the right, where my first coefficient is negative, like these two. Now, okay, you've seen the chart, so I at least wanted to introduce it a little bit that way. Let's look at how we're going to apply this and what you have to do. Got your calculators available still? Graph the polynomial in a window showing its extrema and zeros and its end behavior. Describe its end behavior using limits. Okay? So describe its end behavior using limits. And we're also going to identify how many extrema and zeros because I think it asks us to do that in the book. So if you haven't already, are you graphing A? Now, I always start with the Zoom 6 because I have no idea what it's looking like. Does it look okay with the light on now? Okay. Is his calculator misbehaving again?
I tried to hit Zoom, but it just went into the screen.
Okay. Now, if you watch this, did you see what this graph was doing? Did you kind of watch it graph?
Yeah.
And so you probably know what this looks like. Now, if you didn't watch it or if you can't figure it out, for this one, I'm going to start by doing a zoom out. So after I hit zoom out, I'm going to hit enter one more time. Okay. Now, depending on what you want, depending on what you have to do, if you're happy with this view, you're good to go. If you're not happy with this view, and you want a little bit more zoomed in view, but not zoomed in all the way, this is where I recommend ZBox. I've shown you guys how to use ZBox, I think. Okay, I like ZBox depending on the situation. So ZBox is number 1, and what you do is you make a box around what you're wanting to see on your graph. And so like here, if I just want to see the basic graph and not be zoomed out all the way, make a corner of your square, and then make the diagonal corner of your square, and hit enter, and that's your ZBox. Okay. If you're fine with the previous graph, then you don't need to do that. But if you want a better view, that gives you a better view. Okay. So we have an idea of what we're looking at here, right? And I am, as a reminder, I'm writing ZBox at the end of those directions. That way if you need a reminder of a good way to graph it. So, before we get into talking about the limits, I should have asked before we started, but okay. Based on, if this is degree 3, should have phrased that differently too. Okay. Do we agree this is degree 3? I should have made it a question.
Yes.
It's a power of 3, right? Based on degree 3, at most, how many extrema could we have here? 2 extrema, yes? Because extrema is the one that is 1 less. Do I have two extrema? Yes, because I have a min and a max. So if you're asked how many extrema you have, you can hopefully identify that there are two extrema. In this particular case, there's a min and a max. Zeros. If this is degree 3, at most, how many zeros could I have? 3. If it's degree 3, you can have at most 3. It's the same thing. Remember, zeros are another way to think about solutions. And if it's degree 3, we can have up to 3 solutions. How many zeros do I have here?
3.
I have 3. We have 3 zeros. 3 places we're crossing the x-axis. Okay. Now, looking at in behavior using limits. Let me write out, because notation. Notation is important here. You have to be able to write proper limit notation. I don't know, have we really written limits before? I don't think we have. Again, I get my classes confused. So the two questions we're going to be asking ourselves for in behavior. The limit as x approaches positive infinity of f of x. That's one thing we're going to be asking. And then the other thing I'm going to be asking is the limit as x approaches negative infinity of f of x. When you have to talk about in behavior using limits, these are the two questions you ask yourself every time. Because in behavior is as we go infinitely left and infinitely right. Okay, I'll give you a moment to write down notation. Then we're going to talk about this. So, as x, this says the limit as x approaches infinity. What does that mean? As x approaches infinity. Which direction am I going on the graph then? As we move to the right. So this is asking, as we move to the right, what is my graph doing? So as I move to the right, where's my graph going? Up. How do I answer using not the word up, but the appropriate symbol? It's going up to positive infinity, yes? So you can say up. I'm okay with us saying up, but what do we need to write? Positive infinity. Does that help explain it a little bit? So now, the second question says, as x approaches negative infinity. So what's that asking? As x moves left. So in this particular problem, as x moves left, where's my graph going? Down. What should I use to say down? Negative infinity. And again, I'm throwing in those words left, right, up, down while we get this all straightened out in our head of how this works. Does your notation look similar to mine? This is official limit notation. We use this in pre-calc. It's a big deal in calc. So it's limit notation you have to get familiar with. When I ask you to write limit notation on like a quiz or a test or something, I'll be looking for you to go for this form. Okay? This is not, you get to pick your own form. Good. Can we do the same thing that we just did on A on B? Maybe you guys guiding me more this time? Okay, get them graphed. Can you guess more what this graph looks like? Taylor Swift, we are not. Two x to the fourth plus 2x cubed minus 22x squared minus 18x plus 35. Okay, I might go back to Zoom 6 because who knows, you wouldn't go to Zoom 6. Yeah, I know I have to zoom out and then Z-box. Okay. And again, if someone wants to argue I can tell where the lines are going. I watched it graph. Then I get that. If you don't want to waste your, take your time to zoom out and figure out what it looks like. But if you're not sure, or if you just want that better visual, I do a zoom out so I can get all of it on the screen, and then I will Z-box it if I want a closer image.
Oh no.
Okay, now, and technically, I think all of mine's on the screen. I can't even tell. Height-wise, I'm about good. It's just I need to change my width pretty much. But if I pretty much go all the way to the top, set my top corner, and then diagonal corner at the bottom, I think I get pretty much all of it. But even just making it wider, you get a better image. Okay, I'm missing one little bottom piece. I'll take it. It looks good enough to me. Okay. So what degree is this problem?
4.
Degree 4. What do you expect in the way of extrema if it's degree 4? At most 3. What do we have on this one? We have 3, yes, because what do you see? 2 mins and a max. Okay. If this is degree 4, how many zeros do you expect?
4.
At most 4, because it means there are at most 4 real solutions. What do we have in this case? Do I cross the x-axis 4 times?
Yeah.
I do. Okay. Can you write your limit notation to begin with? And I don't care which one you do first. I'm just going to go in the same order. The limit as x approaches infinity. Limit of f of x as x approaches infinity. We're going to write what that equals. And the limit of f of x as x approaches negative infinity. And based on the fact, this is x to the 4th, yes? If it's x to the 4th, if we use our algebra 2 words, what do we know? My end behavior is either going
Up or down.
up, or down, down. Because it's a positive 2x to the 4th, what are we expecting to happen?
Up.
Up. So if you know that much, you could probably tell me, what is that in terms of the answers we're going to give? They're both positive infinity. Now, that's what it's asking. As x approaches positive infinity, that's saying as x goes right. Where's my graph going? Up. And up is represented with positive infinity. As x approaches negative infinity, that's saying as we go left, where's my graph going? Up again, which is positive infinity. Again, I'm not against you thinking in terms of left, right, up, down, but final answers are in terms of limit notation and using infinities. Okay? Does that look a good thing or a bad thing? Oh, crud, I had the wrong time in my class. What time we're 14, aren't we? Okay, that is a perfect ending point. I was confused. I was thinking 22 was our ending time. I was on 5th hour.
Yeah, that's how it is.
I know. Okay, listen. I really thought I was going to have time to get into the next part. Okay, so here's where we're at. First of all, if you didn't notice, Tuesday has one page, 193 assignment. Wednesday has the other. Those are the 2 assignments for all of lesson 2-3. I will not add any more tomorrow. In all honesty, you can definitely get through all of Tuesdays. I don't know that we've done a whole lot for Wednesdays or not. So, I will teach notes tomorrow, and everything will be due Friday. Got it? I would encourage you to start working through it so you're not complaining about me Thursday night when you have a ton of homework to do. Just saying. Because this is all week. Yes.
Oh, it's okay.
Oh, that's fine.
What? I did. Okay, hold on. Just can you give me half a second to stop this?